maybe I think we can start. So it's a great pleasure to introduce Professor André Neves from the University of Chicago, who is going to talk today about area rigidity of minimal surfaces. Thank you, André.
Okay, so I want to thank the organization for the invitation. As I think last time I was at IMPA, maybe I'm going to go 2015 or 2014. So it's been a long, long time, and it's a pleasure to be here. So I'll talk about the ongoing work I've been doing with Fernando and with Lucas. So I'll start with a brief introduction. So on a closed manifold, the minimal hypersurface, they are defined as being critical points for the area functional. And this extends the notion of geodesics on a surface. And minimal surface are a central topic in geometry, mostly because there are a lot of problems in geometry which do not involve minimal surface, but if you want to understand them, we need to delve deep into the theory of minimal surface. For instance, the most famous one would be obstructions to metrics, obstructions to manifolds having positive scalar curvature. So minimal surface, or the study of minimal surface, provides those obstructions. But there are many other instances. Of course, in the work of minimal surface, the theory of closed geodesics has been a constant source of inspiration, but there's a fundamental conceptual difference. And the difference comes from the fact that geodesics, they can be defined in two distinct ways. They can be defined as critical points for the energy or for the length functional. And this is the way that minimal surface, they are defined. They are defined as critical points, is what we call the variational way. But geodesics, they can also be defined as periodic orbits. To closed geodesics, they can be defined as periodic orbits to a Hamiltonian flow, which is a geodesic flow. And this definition also plays a huge role in the theory of closed geodesics, especially when the manifold has negative curvature, because when the manifold is negative curvature, this Hamiltonian flow gets some extra property, which is in this case an on-off flow, and that puts a lot more structure on the space of geodesics. And so the challenge in minimal surface is that we draw inspiration from geodesics, but most of the proofs do not apply, because many of the proofs of theorems for closed geodesics, they rely on this interpretation of geodesics as being orbits to a Hamiltonian flow. Okay, so the fact that geodesics have essentially two distinct definitions, it means that they are more rigid. And if they are more rigid, it means that there are less geodesics than minimal surface. And so one particular case is just to see what happens on comparing the three-sphere with the two-sphere. So on the two-sphere, the closed geodesics, they are the great circles. They are intersections of the two-sphere with a plane passing through the origin. But on the three-sphere, if we look for minimal surface, then in that case, the analog of the great circles would be the equators, the intersections of the three-sphere with a plane in R4, with a hyperplane in R4 passing through the origin. Those give you equators. But on the three-sphere, you can have many more minimal surface, which are not the equators. And actually, it's a celebrated result of Lawson that on the round three-sphere, you can have an embedded minimal surface of every possible genus, provided it's orientable. So philosophically what this says is that there are a lot more minimal surface than there are geodesics. Oops. Okay. So regarding geodesics, a famous question was asked by Poincaré in 1904, and he asked whether every sphere has at least one closed geodesic. And this question was eventually fully answered, spanning a period of more than 60 years. And answering to this question, it led to many developments in modern mathematics, of course, calculus of variations, dynamical systems, Morse theory, and so on. Motivated by this question and by the subsequent results, which essentially show that on any closed surface we do have an infinite number of closed geodesics, yeah, we conjecture that on every closed tree manifold we should also find infinitely many closed minimal embedded surface. And so now I'm going to make an important disclaimer, is that all manifolds I'll talk here, they have dimension at most 7. And the reason why I'm going to do this is so that I don't have to address the issue of minimal hypersurface having possible singularities. So by the time that Yao conjectured that on every tree manifold we should find infinitely many minimal surface, it was shown by Pitts and Shane Simon. They showed that on any closed manifold we can always find at least one minimal embedded hypersurface. They did this in the 80s, and then there was a long period of no progress. But fortunately, over the last 10 years, the Yao conjecture was fully settled, thanks to the combined work of Yevgeny Lukumovich, Fernando, myself, Antoine, and Shinjo. And so the combined work shows that on any closed Riemannian manifold, assuming the dimension is 3 or higher, and of course less than 7, we can find an infinite number of distinct minimal embedded hypersurface, sigma k, and they have the following property. For a generic metric, the Morse index of sigma k is exactly k, and the area of this minimal surface, it goes to infinity. So if we divide the area of sigma k by the n plus 1 root of k, then the limit obeys the Veil type law, which means that the limit will depend only on the volume of the manifold, in the same way that if we divide the Laplacian spectrum by the growth rate, we get a limit which is universal, depends only on the volume. So there's a concept here that I did not define, which is the Morse index of sigma k. And so the Morse index is an important number that we associate to any critical point. In this particular, we associate to a minimal surface. And what it counts is how many distinct ways do we have of decreasing the area of a minimal surface. For instance, if we go on if we take a torus and look at this geodesic, then in this case the Morse index is 0. Because every perturbation we do should increase its length. But if we go to the equator and look at this geodesic, then the Morse index is 1. Because if we push the curve down, we will decrease its length. And so this number, and maybe it's harder to imagine, but if we think about it, it's easy to come up with examples where you pick some large number k and you can find that surface in which you draw a geodesic, and that geodesic will have k distinct ways of decreasing the length. Okay. So let me tell you briefly what's the principle behind finding this minimal hypersurface sigma k, because that's going to be important to the results I want to show you. So what I want to explain is, I stated this result that every closed manifold admits an infinite number of minimal embedded hypersurface. So I want to say what's the method behind finding this sigma k. So the way you do this, we use a variational method. And so the way the method works is, first you're going to make an educated guess of what the area of sigma k should be, and then when you have an educated guess of what the area should be, then you use some machinery to show that your educated guess can actually be realized by the area of a minimal hypersurface. It's exactly like variational methods work. So if you want to find a minimum, first you make sure you have an idea of what the minimum value would be, and then you take a sequence and you show that that minimum value is realized by indeed a minimizer. Okay, so let's see. Shinzo, he talked about this yesterday, but I will review it. So the starting point is that Almgren, he showed in the 60s that we fixed the manifold M, and we look at the space of all trivial closed hypersurface. So this is the space of all boundaries of regions on the manifold. So you take any manifold M, this is an incredibly big space. It's an infinite dimensional space. And what Almgren showed, as Shinzo explained, is that this space is weakly homotopic to RP infinity. So it's an incredibly big space, but it admits a 2 cover, and that 2 cover is contractible. And so each space which has a 2 cover and the 2 cover is contractible, it's denoted by RP infinity. It's a K pi 1. So in particular, the cohomology or the homology of this space has to be the same as the homology of RP infinity, which is known to have just a single generator. So H1 of RP infinity with coefficients mod 2, that's non-zero. And then if you do cup powers with that, you generate every element in the cohomology. So the important thing to retain from this is that we have this space, and this space contains a lot of topology. Okay? So now we fix the metric G, and minimal hypersurface, they are defined as critical points of this functional. So you take an element there, which is a boundary of some region, and you just compute the area. So it's just the area functional. Okay? So now we're going to do the following little thought process. So on this infinite dimensional space, I look at all elements where the area is very small. So if L is a very small number, I look at all elements with a very small area. That space is contractible. And so if it's contractible, it means that if I look at this element, this, it's not a form. It's not a form, right? It only exists in singular cohomology, but let's just, for the sake of the argument, say that this is some K form. Then this K form should be exact on this space, or it's going to vanish when L is very small. If L is very large, then this space is practically everything. And so if it's practically everything, of course, this element cannot be 0, because we know that the kth cohomology of the space is non-trivial, and this is the only generator. So this is non-trivial. So the educated guess for the area is to take the first number where this space goes from non-detecting lambda k to detecting lambda k. So if I were to draw a picture, the canonical picture is the following. So we imagine this is Z. What was the notation I used? Yeah. So we imagine that this is the space. This is the area functional. And so if I take some L small, this is small L, then the inverse image is this set, which is contractible. If I take something big, like here, then the inverse image is going to be this part, which is clearly non-contractible because it has a pi 1 there. And so there's the critical value here, which we call omega k, where it's this critical parameter where L goes from, it changes topology, right? It's going to be this space. And this is the area of the critical point. So it's exactly what we are doing here. Okay? So we record the smallest L for which has the property that this space will detect lambda k, and we call that omega k. And so this non-decreasing sequence, that's called the volume spectrum, and it shares many striking properties with the Laplacian spectrum, as we saw in Shinzo talk. And so the overall, content of this talk is to see to which extent this volume spectrum determines the manifold. Of course, for the Laplacian spectrum, that's a well-known question. And so we are trying to see to which extent does the same thing hold for the volume spectrum. Okay, so if you want to see whether this volume spectrum, which is the sequence of numbers of where each number should be realized by some minimal hypersurface. So if you want to see if that determines the metric, it's important to see what happens for closed geodesics and to which extent can we recover the metric on a surface by the knowledge of the length of its closed geodesics. So for surface, that's a reasonably well understood problem. And the answer depends on the curvature of the ambient manifold. So if we have a negatively curved metric on a surface, then it's known that the length of the closed geodesics determines the metric. So this was proven by Otal and separately by Croak around the same time. So for negatively curved metrics, the length spectrum determines the surface. For flat metrics, it's a theorem of Bangert that if you put any metric on a torus, and if its length spectrum is identical to the length spectrum of some flat metric on the torus, then that metric you start with has to be isometric to that specific flat metric. And for positive curvature, there's a canonical example. They are called the Zoll metrics. And the importance of this example is that it says that you cannot recover a metric from the knowledge of the length of its closed geodesics if the manifold is positively curved, because it's possible to put metrics on the two-sphere. I think the first person was Zoll, so they are called Zoll metrics, which have the property that every geodesic is closed and has length 2 pi. So it has the very same geodesics as a round two sphere has, but the metric is not round. So which means that you cannot recover the metric from its closed geodesics. Okay. So in that regard, so Mark Skuo last year, he showed that if we look at Zoll metrics, which can be connected to the round metric on S2, that for those Zoll metrics, if we compute the volume spectrum in this way that I defined 2 slides ago, then the volume spectrum is going to be, we get this sequence of numbers, and that sequence of numbers is going to be exactly what you get for the round S2. So what this says is that we cannot determine a metric on a surface by the knowledge of its volume spectrum in general. But on the other hand, the guiding principle that Fernando and Lucas and myself are following is that on the sphere, on the n-dimensional sphere, there are many more minimal hypersurface than just the corresponding equators. So for this reason, because there are many more minimal surface, we hope that the volume spectrum of the sphere should be rigid, because if a manifold has the same volume spectrum of a higher dimensional sphere, that means much more than having the same volume spectrum as the two-sphere, because the geodesics on the two-sphere, they're essentially boring. They're just circles, while the minimal surface on the n-sphere, they occur in a much wider variety, like their topological type is not determined a priori. Okay? So, but in any case, if we want to understand the rigidity of the volume spectrum of the n-sphere, we have to understand this Zoll matrix. And so 2 or 3 years ago, we came up with this definition of codimension 1 Zoll. And so this is the analog for Zoll matrix, but for minimal hypersurface. So the definition is the following. Let's fix the n-sphere. We already saw this definition on yesterday morning. So we fix the n-sphere, and we put symmetric G. We say this metric is codimension 1 Zoll if it has the following property. If I can find a RPN family of minimal hyperspheres, which have the following property. If I pick a point P and n-1 plane passing through that point, I have exactly one minimal hypersphere with its tangent to that plane. So with this definition, let's make sure that the round sphere or the round metric on the n-sphere, that's a codimension 1 Zoll metric. So we need to say what the family is. So here's the round sphere. We pick any point V. That's a unit vector. This point V defines a hyperplane on Rn plus 1. And if I intersect that hyperplane with the n-sphere, I get sigma V, which is going to be a n-1 hypersphere in Sn. Okay? And now, this, of course, if I take V or its antipodal point minus V, the hypersphere is the same because we just changed the orientation, but the plane is the same. So, which means that this family sigma V of equators is in fact being parametrized by a RPN. So we got that out of the way. So we get that this family sigma V is parametrized by a RPN, which is the unit vectors with an antipodal map. And now it's easy to see that this family has the property we want, that if we take any point, so you can see this for geodesics, right? If you go on the two-sphere, you take a point and a direction, there's exactly one closed circle that passes through that point with that direction. So that's a codimension 1 Zoll metric, okay? And so the Zoll metrics, they were heavily studied throughout the 70s and the 80s. And Gilman has an important result there, where Gilman showed that if we pick any odd function on the two-sphere, then we can find a one-parameter family of Zoll metrics of the following form. 1 plus TF plus higher order terms. What this means is that this is a one-parameter family that starts on the round metric, and the deformation is determined by this odd function. Okay? So what Gilman result is saying is that there are at least as many Zoll metrics as there are odd functions on the two-sphere. And the motivation, of course, was that many years before Funk, he had shown in 1913 that if we have a deformation of the round metric by Zoll metrics, and if we differentiate the deformation, that the function you get has to be an odd function. So Funk had showed that F odd was necessary. Gilman showed that it's sufficient. Okay? So Gilman's method was based on the interpretation of geodesics as periodic orbit Hamiltonian flow. And so the way he does is he wants to find deformations of the round metric, which have the property that the geodesic flow for the new metric is conjugate to the geodesic flow for the round metric. If you can do that, it's a basic property of conjugate flows, that they're going to have the same periodic orbits and the period is going to be the same. So that solves it. And Gilman, he does this using implicit function theorem. So 3 years ago, jointly with Lucas and Fernando, we extended Gilman's result to the context of codimension 1-Zoll matrix. And so we show that for any symmetric two-tensor H that we pick, and the symmetric two-tensor should be of the following form. We have the round metric, and in front of the round metric, we multiply by odd function. Then we have the Lie derivatives and some transverse traceless tensor. So for every tensor of this form, then we can find a codimension 1 family of Zoll matrix, G of T of the form G naught plus TH plus higher order, and we show that this condition is also necessary. So this would be the analog of Gilman's result for the context of minimal hypersurface. Of course, Gilman's proof does not apply because the way we produce these codimension Zoll matrix is not by finding conjugate flows, because the interpretation does not make sense. So we also use the implicit function theorem, but we had to devise a new method to produce those. So this year, Ambrosio and his student Guaiardo, they found that you can actually find this codimension 1-Zoll matrix that can be isometrically embedded in Rn plus 1. So for instance, the only picture, okay, so the picture I had 2 slides ago of the Zoll matrix, that was isometrically embedded in R3. And so there, the result is saying that we can also do that generally. Okay, so now I will present you the results I want to talk about. And so we need to change the space a tiny bit. So on the 3 sphere, we can, of course, consider the space of all boundaries of regions, but that's not the, that's a useful space. But there's another interesting space to consider, which is the space S of all embedded 2 spheres in S3 with a point added. Of course, any 2 sphere in S3, it's going to be the boundary of a region. And so this smaller space is included in the bigger space. And one can show that this bigger space, the space of all embedded 2 spheres, so it's contained inside the space of cycles, and the important property it has is that it detects some topology of the space of cycles, because Hatcher is showed in the proof of the Smale conjecture that the space of all embedded spheres with an added point can be retracted onto the space of all geodesic spheres on S3 with the added points, and the space of all geodesic spheres on S3 is parameterized by RP4, because they are parameterized by the center and the radius. And of course, if you take a center and the antipodal center, and if the radius is pi halves or pi, then they're going to parameterize the same guy. And so what this means is that this space of all embedded 2 spheres detects lambda 4, or lambda 4 is non-zero on that space. And so if this smaller space still detects topology, we can, in the same way that we define the volume spectrum, we can consider the spherical spectrum or spherical width. And the definition is the same. We look at these 4 numbers, 1 to 4, that they are defined as the following way. We take the smallest number L, where the space of all spheres of area less or equal than L still detects lambda k. Okay, so it's the same definition as the volume spectrum. The only difference is that the space L does not have lambda k non-zero for very large k. Actually, lambda to the 5th is 0, so it stops at k equals 4. And so we only get 4 numbers. Of course, the spherical spectrum, or the spherical width, and the volume spectrum, they are very much related. Okay? And so regarding the spherical width, I'll tell you about what are the 3 basic structural results for the spherical width. So Shinzo, yesterday, he talked about the basic structural results for the volume spectrum width or the min-max width. But as we might guess, the theories should be analog because the basic principle behind the theories are the same. We have a space with topology, we have a functional on the space of topology, and we are finding critical points. So the first basic structural result that was proven by Simon Smith, or it was Smith PhD thesis, Simon was his advisor, and it's what we refer as just the min-max theorem. And it says that if we pick any number k between 1 and 4, then we can find sigma k, a closed embedded minimal sphere with possible multiplicities and possible disjoint connected components, such that the area, the total area of sigma k, is realized by that number sigma k, and the Morse index of sigma k is less or equal than k. So it's possible that sigma k could be the disjoint union of two spheres, sigma 1 and sigma 2, where the first sphere comes with multiplicity 2, and the second sphere comes with multiplicity 3. So a priori that's possible. This is this issue with multiplicities is a serious drawback on the theory, but fortunately there comes the second basic structural result. This was proven by Zhou and Wang last year, and it's the multiplicity 1 theorem, and it says that each unstable component of sigma k will have multiplicity 1. So if sigma 1k is unstable, meaning if we can decrease its area locally, then this will have multiplicity 1. And then if this one is stable, then it could have higher multiplicities. So this is a important result for the theory. And then the third important result, I'll come later because the statement is a tiny bit more technical. It's the Luschnik-Schnirelmann property. And so what we're going to do is I'm going to present you the first result, sketch the proof of half the first result, then tell you about this third property, and then when we know the third property, then I'll sketch the rest of the proof for the result I want to show you. Okay. So the first result is what we call theorem 1, and the result is the following. If you take any metric G for which the first spherical width, so then the first spherical widths are the same if and only if the metric is a codimension 1-Zoll metric. So as I said, geodesics, they are always the inspiration for a lot of results on minimal surface. And so the analogous theorem for Zoll metrics on S2 was proven several years ago by Mazzucchelli and Schur. So what I'm going to do now is I'll tell you, let's see how does this direction work, which is let's suppose that we have a metric which is codimension 1-Zoll or surface Zoll. Let's consider its Zoll family, and let's make sure that the spherical widths have to be identical, okay? So, let's start with some remarks. So we have this RP3 family of minimal embedded spheres. So the first remark is that they all must have the same area, because if you have a continuous family of minimal surface, you differentiate the area, the derivative is going to be 0, and so the area function is constant. So they all have to have the same area. They will all have some kernel, because if you have a family of minimal surface, then if you differentiate that family, it means that you're going to have an element in the kernel of the second variation, and what this means is that they are all unstable. Okay? And the third property is that any two elements in the family must intersect, because if you had two elements which were disjoint, it's a continuous family, then you fix one element, and then you move the second element until it first time it touches the first element, but it's a basic property of minimal surface that they cannot touch tangentially. Or they cannot touch tangentially where one is to one side of the other. And so this would force them to be the same. So they have to pairwise intersect. And so there's an important result we used here due to Galvez mirror, which says that no other, it says that if you have a whole family, then every other minimal sphere on S3 must be one element in the family, okay? So now the ingredients we have is we assume the manifold is all. So we know from Galvez mirror that that gives us all the minimal spheres. And we also know that they are all unstable and they all must intersect. So the min-max theorem would say that these numbers sigma k are going to be some summation of areas of minimal spheres, but all minimal spheres are on this family. And so, and they all pairwise intersect, so it means that we can only get one with some possible multiplicity. And so the min-max theorem will imply that all the sigma k's have to be some multiple of L, some integer multiple of L. But now, of course, the multiplicity 1 theorem, because they're all unstable, says that the multiple is 1. And so we get that all these four numbers are identically L, and so they all, the spherical widths are all identical. So this proves one direction. What I'm going to do for the next 5 or 6 minutes is to prove the other direction. But before I do that, I have to show you the third ingredient that's missing, which is an important structural result on the variational theory of minimal embedded spheres. So let's set Vk to be the set of all minimal spheres with the area sigma k and Morse index less or equal than k. So by the min-max theorem, I know that this space is non-empty. It has at least one element. Now, this result is what we call the Lushnik-Schnirelund property. We proved this for the other, we originally proved this result for the Almgren-Pitts min-max, but the same proof essentially applies for the Simon-Smith min-max, and actually in Zhou Wang paper in the appendix, they do carefully the whole argument there. So the setup is the following. Let's assume that two of these numbers are identical, say the second width and the fourth width, that we happen to have the same number. So then, in this case, what this result says is that Vk detects lambda p. So if k is 2 and p equals 2, then this would say that Vk detects lambda 2. So in particular, Vk cannot be a single element, because if it were a single element, it should in no way detect an element that lives in the second cohomology. So in particular, what this result says is that if two widths are identical, then this set Vk should have some p-dimension like qualities. So the motivation, this result is identical to the following standard result on the Laplacian spectrum. We know that if, say, the second eigenvalue equals the fourth eigenvalue, then we know that we have a two-parameter family of eigenfunctions which all realize the second eigenvalue with multiplicity 2, right? So, of course, so this is the analog of that result, but of course, we don't have vector spaces or linear spaces to talk about. So this is the analog of that result, but instead of saying that we have a two-parameter family of eigenfunctions, the way we say is that the space of critical points realizes lambda 2. So lambda 2 does not vanish there, where lambda is the generator of the singular cohomology of the space. And using the vanishing lemma, this property implies the following. So that given any p points on the tree sphere, then we can find an element sigma k in this family, which has the property that it passes through these k points. Okay, so this is using the vanishing lemma for the k power. But the thing to retain here is that when two of these numbers are identical, say if the first equals the third or the first equals the fourth, then we should have some two-dimensional or three-dimensional family of critical points. So that's the basic philosophy. Okay, so now let me sketch you the proof of this direction. So for any, what I want to sketch the proof now is the following statement. If you take a metric G such that the first four widths are identical, then the metric is codimension 1 Zoll. So we start with the first four widths identical, and to make our life easier, let's just assume that the metric has positive Ricci curvature. So positive Ricci is useful because it immediately implies that when you do the min-max theorem, you only get one connected component, and because of the Zhou-Wang result, it also implies that they all have multiplicity 1. So under positive Ricci, our proof can be streamlined considerably. So let's just assume that. So we need to find the Zoll family, right? So the first obvious candidate is to take the Zoll family to be V1, which is the space of all minimal spheres with Morse index exactly 1. So the min-max theorem says that the first width has to be equal to the area of some element there. So in particular, we know that this set will be non-empty. The theory, in general, it only says that you get an element where the Morse index is less or equal than 1. But of course, we are assuming that it's positive Ricci. There's no element, there's no minimal sphere with a Morse index 0. And so if it's less or equal than 1, it's exactly 1. And so this is, and so we get a little bit of advantage there. So that is the first guess. Now, but it turns out that we can pick a better candidate for the Zoll family. And so the better candidate is to choose the elements in V1. I call G for good. So this is the good set. So this is the elements in V1 which have the following property. Their nullity is 3, so they have a three-dimensional kernel, as you expect. And the nullity is integrable, meaning that not only you have a kernel, as you can realize the elements in that kernel by a family of minimal, by a three-dimensional family of minimal spheres. Okay. So there's an important result here due to Chang from many years ago, which says that its result is that if you put a metric on a sphere, okay, and you use any Schrödinger operator, then its result is that the first eigenvalue, there's an upper bound on its maximum multiplicity that's determined by the topology. In the case of the three-sphere, this means that if you have a minimal sphere with index 1, then its nullity has to be at most 3. This is important because this means that this subset G is an open three-manifold. Okay? Because we take an element G, what we know is that it has nullity 3, and it spans the three-parameter family, a small three-parameter family of minimal spheres, but an element in this three-parameter family might, an element in this three-parameter family will have nullity for sure 3, but it could be 4 or higher. And so if it were 4 or higher, then we could not find shards on G. But on the other hand, we know that because it's there, every element in this family, so you take the guy which has nullity 3, it spans a three-dimensional space of minimal spheres. Every element in that subspace has to have nullity 3 as well, and so it's contained in the family. So what this means is that this family G is a three-manifold. So this is important because a priori, the only thing we know about this set is that any open neighborhood detects lambda 3, but that's not enough to say that it's a three-manifold. There's a canonical example, right? There's a canonical example of a set whose open neighborhood detects lambda 1, but it's not a manifold, right? The canonical example is this. Just do on the plane, take a point here, and now we consider a circle like this, and then we start oscillating a lot, and we increase the oscillations until they accumulate here on a stretch, and we do the same thing from that side. So if you take any open neighborhood of this set, then it's non-contractible, right? It's going to be an annulus. So that detects lambda. On the other hand, it's not this set has a property that it's not a closed manifold, right? So there's no, it's a circle, but it's not a closed manifold. It oscillates there infinitely many times. So the challenge is to show that this space eventually will be a smooth three-manifold, and so we have to go by steps. The first step is we identify that a set which already has a structure of a three-manifold, so that's the way to go. And now the challenge is to show that the set is non-empty and that it's closed, okay? Because if the set is non-empty, it's closed, then this set, what is called the good guys, then that will be the perfect candidate to be the Zoll family. So let's consider then the bad guys, which is everything every minimal sphere of Março index 1, which are not in the space G, right? So they might have nullity 3, but it's not interval. So the main computation we do, so we use Major-Viatori sequence to show that if we take an element there on this bad set, we can find a tiny neighborhood which has the property that if I remove that neighborhood from the original set of minimal hypersurface, that will still detect lambda 3, okay? And so if we do this, we argue inductively because V1 is compact, so we can argue inductively, and so we start removing bad points from V1 until we eventually get that lambda 3 will vanish, will be non-zero on the set G, and so G is a three-manifold, and what this means is that it has to be non-empty, and it's closed, because if you had an open three-manifold, lambda 3 is going to be, if you have a manifold which is not closed, then H3 vanishes. And so we have that lambda 3 is non-zero, and so it cannot vanish. And so as soon as we got our hands on a closed three-manifold, then the problem becomes standard. So from Luschnig-Schnirelmann, we know that through any 3 points, we can find an element there which passes through these 3 points. And so using the 3 points carefully, which is you fix one point and you make the other 2 converge to this point in different directions, and you look at the minimal surface that passed through these points, then using this property, we can see that through every 2-plane, we can find an element in the good set which has the property that the tangent plane to that minimal sphere is exactly the plane you picked. And so as soon as you have that property, some extra work will show that indeed this family is diffeomorphic to an RP3, and this is a Zoll family, and so this is how you finish the problem. So I still have 10 minutes, so what I'm going to do on the 10 minutes is left, I'll just present the other results. There will be no proofs, and I will present, I'll talk about several conjectures and open questions that we have about this direction, because I think this is an exciting new direction to take. So the hard part of the talk is over. Now is just more intuition stuff, okay? So the first conjecture we have is that we conjecture that the volume spectrum of the three-sphere should be rigid, meaning if you have any other three-manifold which has the same volume spectrum, like the full spectrum, not the spherical width, if it has the same volume spectrum as S3 with this canonical metric, then that manifold has to be isometric to the S3 with the canonical metric. We saw that for the two-sphere, that's not true because of this Marx-Kuo result. And so this is what makes this problem, this conjecture, interesting, in my opinion. So the second conjecture, so the philosophy behind these problems is to understand to which extent the volume spectrum determines the manifold. So the second conjecture we have is that if the first four elements of the volume spectrum are identical, then that should fix the diffeomorphism type of the manifold. So if omega 1 to omega 4 is, they're all identical, then the manifold should either be the three-sphere or RP3, okay? So meaning the way I want to say this is that we conjecture that the volume spectrum detects the diffeomorphism type of the manifold. So now there's an interesting question here, which I imagine maybe it's not so hard to answer. And the conjecture is that among the conjecture is to classify among the homogeneous matrix on the three-sphere, the ones which are Zoll. I imagine the conjecture is that only the Berger spheres are the homogeneous, that among the homogeneous matrix on the three-sphere, the Berger spheres are the uniques, are the only ones which are codimension 1 Zoll. So the next two questions, they are purely topological, but the motivation is the following. So there was a period where there was an intensive study on the properties of Zoll matrix. And so one thing that people wanted to understand at the beginning, and there's actually a conjecture about it, is if you know that a manifold has the property that the unitangent bundle, so if you take a manifold and you assume that every geodesic is closed and they all have the same length, you want to nail down the diffeomorphism type of the manifold. I think the conjecture is that if you have a Zoll metric, like a geodesic Zoll metric on a manifold M, then it has to be a compact rank 1 symmetric space. And I think the best result in that direction is that it has the cohomology or the homology of a cross. This was proven by Bott. So the same question could be asked for codimension 1 Zoll. And it's a purely topological question. I imagine that someone should know the answer. And then the question is the following. You take a three-manifold, and you assume that the Grossmanian is foliated by smooth embedded closed minimal hypersurface, meaning if you take any two tangent plane, there's a unique minimal hypersurface that passes through that point tangent to that plane. And so I imagine that forces the manifold to be either the three-sphere or the RP3, but I don't know. I think this is an important question. The other important question is whether one can find a 4-parameter family of smooth embedded hypersurface in the three-sphere, which are a 4 sweep out or detect lambda 4. So the family of geodesic spheres has 4 parameters, detects lambda 4, but it does not work because it contains closed points. So not every element in the family is a closed, smooth embedded surface, right? Because in order to detect lambda 4, you have to include the points. So the family of geodesic spheres does not work. The second example, you could just take some surface, apply the full isometry group, which is SO4. That's going to be a a family with maybe 6 parameters, but that family will not detect lambda 4 because SO4 does not detect lambda 4. So that will not work as well. We conjecture, I mean, the interesting thing of figuring out this question is that if that is true, then you could know that the volume spectrum has to jump for sure every 4 numbers. So you could have omega 17 equal to omega 18 and 19 and maybe 20, but not 21. So every 4 numbers, the volume spectrum would have to jump. So let me also show you some other results we obtained, which are another topic that has been heavily discussed, which is on the systolic inequalities. So as it's been explained, the systole of a manifold is the least length of every non-contractible loop. And so a standard result in that direction is Pugh's inequality, which says that on RP2, you have a sharp bound on the systole in terms of the area. And so this inequality has been generalized in many ways. And one way in which has been extended, of course, is due to Gromov, who proved general systolic inequalities for essential manifolds, in particular for RPNs. And the philosophy is to bound the systole in terms of the volume, but his inequalities are non-sharp. So what I want to show you next is what we believe to be the first sharp systolic inequality for RP3 that works with no curvature conditions. Of course, our point of view is not to bound the systole in terms of the volume, but how to bound the systole in terms of the area of some minimal projective spaces. So let's see how that works. So on RP3, a natural min-max theory is to consider the space of all smooth embedded projective two-planes. So on S3, we consider the space of all smooth embedded two spheres. On RP3, we consider the space of all smooth embedded projective spaces. This has some topology. And so just by analogy with what we did for the volume spectrum and the spherical spectrum, we can consider the projective spectrum, which is you do the same thing. You take the first L so that this set detects lambda k. Now, you still get 4 numbers, but now there's a new difference, which is that the sigma naught, so you start with k equals 0 because the projective spaces, they are homologically non-trivial. So you can minimize there. When you do among regions which are boundary, the minimum is 0, so we tend to not include that. But in this case, sigma naught is the same thing as asking for the least area projective plane in RP3 with this metric G, or you can think about it, or is the same thing as the two systole of RP3 with this metric G. So sigma naught coincides with the two systole. And an obvious inequality one gets between the two systole and the one systole, or sigma naught and the systole, is that we know that the two systole, or sigma naught, it's the area of some RP2. And this RP2 obeys Pugh's inequality, so you get this bound. And of course, if you have a RP2 inside RP3, regardless of the metric, the fundamental group only has one generator. So the systole of the RP2 has to bound from above the systole of the RP3 because it's the same generator. So you get this obvious inequality. And some years, many years ago, with Brendel, Eichmar, and Hubre, we showed that this inequality is sharp, but you have to assume a curvature, a scalar curvature condition, right? So it's not curvature-free. So the curvature-free inequality we show is the following. So we just argued that the two systole is greater or equal than the square of the systole in a sharp way. Now, the theorem we show is that for every metric we put on RP3, we're going to have that the second spherical width bounds from above the Syslo square with a sharp constant, and we get equality if and only if the metric has constant sectional curvature. So we also construct example of a non-round metric on RP3 for which sigma 1 equals sigma 0, which equals the Syslo. And so what this shows is that this theorem is optimal. So the third conjecture we have is that, of course, we conjecture that if the third one equals the first one, then the metric should be codimension 1, but now for projective spaces. And the last question I want to show you is whether one can prove a curvature-free systolic inequality in RP4 in the spirit of this RP2. Okay, so I'll just stop here. Thank you for your attention.